Okay. So yeah. So again, since I have just started recording, so again, just writing an introduction. So this is the last session for discrete maths course. So this is not a problem solving session, but rather a summary session where I'll be giving out basically summary of what we have covered in the 12 weeks so far. So you can just think of it as a story so far kind of lecture. So it will just be a short lecture from a short session from like just 9 to 10 p.m. So just a 1 hour session. So let me just share my screen first so I can share it with you guys. And like maybe at the end of the session, just reiterating myself, if you guys have any doubts or anything left, we can try to address those doubts also, since this is the last session and you'll be having your NPTEL exam after this. So yeah, let me just share my screen. So yeah, so I hope my screen is visible to everyone. So let's just get started with this then. So how I have made this summary session, like this session sheet as, so I have written down all the weeks and all the, like the main theme of what the week, what was the main theme of the lectures of that week, and what were the main things which we covered in those weeks, which basically sir taught in those weeks. So you can think of this as sort of a cheat sheet for the discrete maths course, like all the important stuff packed into like one at one place. So yeah. So in the first week when the session just started, so first week was more about like just a basic introduction, binomial and I guess multinomial theorem. Sorry. So first week was more about introducing again what we have studied in high school already, basic counting arguments and binomial theorem, and so some new things like Cutler numbers also. So one thing which we covered was what are permutations. So permutations are denoted by NPR, and what this means is number of ways in which R items can be selected and then ordered out of the N items. So basically, suppose we need to select R items out of N items and then order them also. So that is basically the what permutation means. And the formula for this is given by n factorial divided by n minus r factorial. And similarly, one second, right? So yeah. So similarly, another thing is combinations, which are denoted by NCR. So we pronounce it as N choose R generally. And what this denotes is the number of ways in which R items can be selected out of N items. So note that in combinations, what we do is we just select R items out of N items. So this is given by the formula n factorial by r factorial times n minus r factorial. So what generally happens is, but in permutations, what we are doing is we are also ordering these items. In combinations, we are just selecting these, and in permutations, we are selecting and then ordering. So we have selected R items out of the N items, and now if we need to order them, we need to multiply this by R factorial also, another R factorial. So that will now become N factorial upon N minus R factorial, which is exactly the formula for permutations. So yeah, I'm just trying to make sense, correcting these two, like how these two are related. So these just select and these select and then order. And then we came to binomial theorem. Binomial theorem is nothing but like expansion of x plus y raised to the power n can be written as summation of r, summation of terms from like t, summation of terms tr, where r goes from 1 to n plus 1. And note that this terminology of r term is important because like sometimes like in assignments also a straightforward question can pop out in exam also, like what is the fifth term in the binomial expression, binomial expansion. So it's just like a more of a convention based thing that we are taking R from 1 to n plus 1 and we are defining R at term as this. It's more of a convention based thing. So this is not something which you can derive, rather you have to remember, because uh, it's the expansion for this you can derive, but conventionally naming which term should you call the R at term, should the x to the power 1 term be called the R at term, or y to the power 1 term be called the R at term, or whatnot. So I described this sort of thing in the problem solving sessions also, that this is a convention based thing that we define the R term as n choose r minus 1, x to the power n minus r plus 1, y to the power r minus 1. So you need to remember this, and I would recommend you to remember this because a straightforward question can pop out like in the exam that right the fifth, what will be the fifth term in the expansion. So there you just like there is no derivation for this, it's just a standard convention. So you'll have to remember this. So, so there, as you can see, so there TR term is given by this, and R goes from 1 to n plus 1. So in the binomial expansion, there will be basically n plus 1 terms for R equal corresponding to R equals 1, R equals 2, till R equals n plus 1. So yeah. So after this, we covered the concept of Catalan numbers. Catalan number, which can be written as Cn, is basically defined as the number of ways of going from bottom left to top right of a n cross n square grid by moving only one step right or one step up at a time. So without crossing the diagonal of the square. So this was which we wrote as its formula was given to us as like what this was derived in the lectures also how this is derived. But for now, let's just take it for granted that the formula for this was 1 upon n plus 1 times 2n choose n, which is also written as the basic derivation for this was something like in the derivation we arrived at some formulas in something like this. It can also be written as like 2n choose n subtract minus 2n choose n minus 1. So yeah. So this is the formula for Catalan numbers, which can alternatively be written as this also. Like both these things are equal, you can check by expanding. So one thing to note here is I wanted to point out one thing is so the number of ways of going from bottom left to top right of an n cross n square grid, moving only one step right or one step up at a time. Suppose we had to find number of ways for this only. Like this was not a constraint that without crossing the diagonal of a square. Suppose we just had to find the number of ways for this part, number of ways of going top from top left, bottom left to top right. Then the answer for this would be just 2n choose n ways. Because basically we have to make finally like 2n right steps and 2n up steps, n up steps and n right steps. And now we need to like order these amongst each other. So it will be something like 2n factorial divided by n factorial n factorial. So 2n choose n will be the answer for the total number of ways in which we can move from like in which we can move from bottom left to top right, moving only one step right or one step up at a time. Okay, so and if we now introduce the constraint that we without crossing the diagonal, then the answer becomes 2n choose n minus 2n choose n minus 1. Okay, so suppose you had to count the number of ways of going from bottom left to top right where we pass the diagonal at least once, where we cross the diagonal at least once. So how will you do that then using this much information? So we have been given like without crossing the diagonal the number of ways. Suppose we have to find the number of ways where at least once the diagonal is crossed. So if we introduce like if we have to find number of ways for that part, like if the diagonal is crossed, what we will do is the total number of ways are 2n choose n, and we'll need to subtract the number of ways where diagonal is not crossed. So the answer will be 2n choose n minus of this quantity, which will come out to be 2n choose n minus 1, right? Because 2n choose n, 2n choose n will cancel each other. So the number of ways, this I'm not writing down, but I'm just pointing this fact out that the number of ways for going from bottom left to top right of square grid by crossing the diagonal at least once will be equals to 2n choose n minus 1. So yeah, it's an important observation. I'm not quite sure if this will be asked in the exam or not, but it can definitely be asked. So yeah, and not just exam, but I think it's useful to see it in this manner also. So yeah. And then, so this was something which was covered in the first week. Then in the second week was more about introduction to set theory and De Morgan's law and stuff. So here, basically, first of all, what's the definition of a set? So a set is just a collection of well-defined objects. So this well-defined part is, you don't need to worry about it too much, but just like a set is a collection of objects, you can just think of mathematical objects basically. And mathematical is something which is well-defined. So yeah. And then there was the concept of power set. So power set is nothing but a collection of all the subsets of a set, right? So power set of a set S is just set containing all the subsets of that set. So the cardinality of the power set is equals to 2 raised to is exponential of S. So it's just 2 raised to the power S, 2 raised to the power cardinality of S. And why is this the case? Because every element of S will have a choice of being included or not being included as a subset of the power set, right? So every element has two choices. So, and there are like cardinality of S elements. So the final answer will be 2 raised to the power cardinality of S. So that's why the cardinality of R set is 2 raised to the power cardinality of S. And then there was this concept of De Morgan's law, which just states that A union B whole uh, A union B whole complement is equals to A complement intersection B complement. So it just De Morgan's law only states that whenever you need to take a complement of a complex expression, what you need to do is just replace every union by an intersection and every intersection by a union, and replace all the sets by their complements. So here, like A will be replaced by A complement, union will be replaced by intersection, and B will be replaced by B complement. So it will be A complement intersection B complement. And similarly, A intersection B whole complement will just be A complement union B complement. So this was the basic concepts covered in the second week. Then in the third week, what was covered was mainly Boolean logic and stuff. So Boolean logic, first of all, we understood what are statements, what are, okay, maybe I should add that also. What are statements, what are propositions, etc. So we learned that what are statements, propositions, etc. And so there was question based on this in assignment also, like identify whether some statement, this is a statement or it is not a statement. So yeah. Good. And then we also learned the definition of what is a tautology. So tautology is a proposition. So note that what was a proposition? So proposition was something which is either true or false at a time. As defined in the lectures, proposition is something which is either true or false. It can't be both at the same time. So tautology is a proposition which is always true, regardless of the value of Boolean variables. So example for this would be like P or P bar. P bar I'll denote it as P, not P. Like this is also a notation for complement. Yeah. So example, I would give that. This is a proposition. This is the tautology, because at any time a state either the statement P will be true or the statement not P will be true, right? Because if we set P as like P truth value of P as true, then this will be true or not true, which will true or false, which will be equal to true. And if we set P as false, then also it will be false or true, which will again be true. So this will be a tautology. The tautology is something which is always true regardless of value of the Boolean variables. Here the Boolean variable is P. And then in Boolean logic, like similarly after this, there came similar to sets, there came De Morgan's laws for Boolean form law also. So similarly, like there were De Morgan's law here that here De Morgan's law said that A union B whole complement is A complement intersection B complement. So just replacing union by or and intersection by and operation, we get the same result for Boolean logic also. So what this says is that not of P or Q will just be equivalent to uh, not P and not Q. So I'll just parenthesize all these expressions. Parenthesization is very important, guys, because without parenthesization, order of calculations is not clear generally. So not of P or Q will just be like taking not of P, replacing P by not P, and replacing P Q by not Q, and replacing or by an and. So it will just be not P and not Q. Similarly, for that, similarly for not of P and Q also, it will just be not of P and Q will just be not of P or not of Q. Note their similarities in sets and Boolean logic. Like if you replace intersection by AND operation and union by OR operation, both of these things are called same only. Like De Morgan's law for Boolean formula and De Morgan's law for set theory are same thing. So yeah. So after this, what we have is like after this week three of based on Boolean logic, the week four, the week four primarily focus on relations. So what are relations? So a relation over sets A and B is a subset of the set A cross B. So just take the set A cross B and take its any subset. Any subset will correspond to a unique relation. So that is the definition of a relation. And what are reflexive relations? Reflexive relations are relations in which uh, an element is mapped to itself. Like every element is mapped to itself, right? A comma A belongs to the relation for all A belonging to capital A. Similarly, symmetric relation is a relation in which if A comma B is a part of a relation, then B comma A should also be a part of relation. Note that relations are generally ordered. Like, oh, if I am defining a relation over set A and B, it will mean it's a subset of the set A cross B. And the sets A cross B and B cross A are different sets. So this symmetric relation is defined over, like, let's say two sets. Then if A comma B belong to A comma B and B comma A are different pairs, like they are distinct objects, like A comma B and B comma A are distinct objects. So if A comma B belongs to R, it doesn't necessarily mean that B comma A will belong to R. But for a relation to be symmetric, this should hold true. That if A comma B belongs to the relation, then B comma A should also belong to that relation. Right. And after this, we came to the definition of what's the transitive relation. So transitive relation was something where if A comma B belongs to the relation and B comma C belongs to the relation, then A comma C should also belong to the relation. So basically, like if B is the middleman, as you can see, like B is at the end of a, like if if B is the second element in this and B is the first element in this, then it can get eliminated. The middleman can get eliminated. You eliminate this middleman, and then A comma C should be in the relation. So this is what you call transitive relation. So this is the transitive property. So an equivalence relation, what is an equivalence relation? A relation in which is symmetric, transitive, as well as reflexive. So if a relation has all of these properties, it is reflexive as well as symmetric as well as transitive, then we call it an equivalence relation. And there are some nice properties of equivalence relation, which we covered in just the problem solving session also, that it can be broken down into, it can be partitioned into equivalence classes and stuff like that. And those concepts really help. Like, believe me, they really help in solving problems that relate in computer science, these concepts. So yeah. So note that equivalence relations are very useful for us in computer science. If you study about this in higher studies, like in your future years, then you'll realize the importance. So yeah. And then came week 5. And then what we covered in week 5 was functions, basically. So for in week 4, we studied mostly relations. And now in week 5, we studied functions. So relations are a bit more generalization of functions, or you can say functions is a specific a specific type of relations. So a function is a relation where every element of the domain is mapped to exactly one element of the codomain. So let's say the relations here were defined over set A and B. So relation was defined over this set A cross B, right? A subset of A cross B. Now a function is also a relation only, but here every element of the domain. So here we say the domain to be A and codomain to be this B, right? So every element of this domain A should be mapped to exactly one element of the codomain. Only then can we call it a function. So any subset uh, any subset of A cross B will be a relation, but those specific subsets where every element of the domain is mapped to exactly one element of the codomain, that sort of subset will be a function. That's what I'm trying to say. So every element of set A should have exactly one mapping to set B, right? Note that not every element of set B need not be necessarily mapped to something of set A, but every element of set A must be mapped to exactly one element of set B. And this sort of problem we covered in the problem solving sessions also based on this concept. So this can also be asked in the exam, like identify which of the following is a function and which of the following is not a function. So yeah, note this definition in mind. Keep this definition in mind. And then we came to what is a one-one function. So what is a one-one function? So suppose let's say the function is f. So the one-one function is defined as if f of a is equals to f of a prime is equals to b. So let's say there are elements a and a prime such that both of their values are equal. Uh, f of a and f of a prime maybe. Right this, yeah. So if the value if the function when evaluated at a is equal to function when evaluated at a prime, it should mean that a equals to a prime. So what this intuitively means is that uh, if if an element of codomain is like every pair of distinct elements of the domain should be mapped to distinct values in the codomain. That's what this means. Like if this is a statement, like its contrapositive should also be a statement. So its contrapositive will just be like a not equals to a prime implies f of a not equals to f of a prime. So that is also an equivalent definition for one function. So an equivalent definition for this two-one function is that if for two distinct elements of the domain, they should be mapped to distinct elements of the codomain. So I hope you guys understand what I'm trying to say. So one function is intuitively just a function where every distinct value of domain should be mapped to distinct values of codomain. Yeah. And then comes what's an onto function. So onto function is a function where every element of codomain is mapped by some element of the domain. Or maybe some people like to say that every element of codomain has a pre-image. So that's also the same thing. Like pre-image is just a mapping onto the domain, right? So a function is an onto function if every element of the codomain is contain has a pre-image or like it is mapped by some element of the domain. So note that for a relation to be a function, every don't get confused with the definitions, just keep these intuitive ideas in mind that for a relation to be a function, every element of the domain should have exactly one mapping onto the codomain, right? But every codomain need not have a mapping in the domain. But for a function to be an onto function, so it is onto as well as it's a function. So what this means is that every element of the domain will have exactly one mapping onto the codomain. And also every element of the codomain will be having an image, pre-image onto the domain. So this is an onto function. And similarly, one function, we have already seen that two distinct elements of domain should have two distinct values in the codomain. So yeah. So now what's an invertible function? Invertible function will be function is invertible if and only if it is one as well as onto. So a function like what's an invertible function? Intuitively, it's a function which can be inverted. Inverted means that like f inverse exists. Like, and what does f inverse mean? Like f of f inverse of x gives me back x only. So that's an invertible function, and invert a function is invertible if and only if it is one and onto. Maybe I should write it this way. Invertible if and only if. So this I double F notation means if and only if. So like both ways true. If a function is invertible, then it will be one and onto. And if a function is one and onto, then it will be invertible. So yeah, I think we should sort of learn these definitions in high school also, but I guess it's fine if we have covered this again in the course. So yeah, function is invertible if and only if it is one and onto. So yeah, so this was till week 5. Then in week 6, maybe I should keep this next page. So in week 6, what we covered was principle of mathematical induction. So I don't think I need to elaborate on the topics for that because induction in itself is a very cute idea and like very self-imposed idea. Like you make an inductive hypothesis, you solve one base case, and using the inductive hypothesis, you try to prove for like the next number, right? From Pn, you try to prove Pn plus one. So that's how mathematical induction works. And then the second thing which was covered in week 6 was the pigeonhole principle. And pigeonhole principle is something which I think is quite important to for everyone. Like maybe I'll. Okay, never mind. So maybe you guys can look up the proper statement of what does the pigeonhole principle say. So intuitively, what pigeonhole principle says is that suppose there are k pigeons which have to go into k minus one pigeon, k into k minus one holes. So at least there will exist at least one hole where there will be two pigeons, right? Because k minus one holes need to accommodate k pigeons. So one hole will need to accommodate more than one pigeon. So in this, what we are assuming is one pigeon can only go to one hole, one pigeon does not go to two holes. So yeah, so that's the pigeonhole principle in its intuitive sense, and it's also like very useful in computer science and a lot of applications. So yeah, so most problems are based in week 6 around these two things only. So yeah, and then came week 7, and in week 7, the concepts which were covered were mostly like about related to graphs and trees. So, what first of all, there was like, what's a graph? So, what's the definition of a graph? So, graph is nothing but a collection of vertices and edges. And what are vertices and edges? Like, you guys already, I believe you guys already know what are vertices and edges. And if you are still confused, you can still look up in the lectures the proper definition. This is just sort of a summarizing session. So I'm not going to all the definitions on the formal definitions, but yeah. So what's in edges, you can just intuitively see in a graph what are like what's is just some points and edges are what connect those points, right? And then came the handshaking lemma. So and what does this handshaking lemma say? So handshaking lemma was that sum of degrees of vertices is equals to two times number of edges. So this was the handshaking lemma, which was discussed in lecture also. And it just states that sum of degrees of vertices in a graph, sum of degrees of all vertices will be equal to two times the number of edges of the graph. So this is the handshaking lemma, and it is also quite useful. Suppose you have been asked that the so you have been given degrees of all the vertices, right? But you have not been given the actual graph, but you have only been given that the degrees of all vertices of graph are such and such and such, and you need to find what will be the number of edges in that graph. So you can just use this formula, sum up the degrees and divide by 2, and you'll obtain the number of edges. So yeah, so this is handshaking lemma. And then came Havel-Hakimi theorem. So Havel-Hakimi theorem was to find out whether a given sequence of numbers correct. So Havel-Hakimi theorem was mainly used to find out whether so its theorem was like very straightforward and like and the main aim for of this theorem was to find, so this gave us a very easy algorithm to find out whether a given sequence of numbers. So if we have been given a sequence of numbers, so whether that sequence is basically, I think, graphic or not, what they say. So what it means was that whether that sequence of number can correspond to degree of vertices of a graph, of some graph. So basically what this answers is the question that given some sequence of numbers, does there exist a graph uh, whose degrees of vertices are this sequence of numbers only, the sequence which we input. So Havel-Hakimi theorem basically gives us an algorithm sort of, which tells us which will tell us like if some sequence can be degrees of vertices or if some sequence can't be degrees of vertices. So yeah, it's also quite useful. And one important point I'll again make is, which I made in this previous session just 1 hour before also, like always remember to sort the sequence in descending order at every iteration of so yeah, this is something like I have been stressing a lot on this because a lot of people forget about this, believe me. So like in Havel Alchemy, what we do is first of all, we sort the sequence in descending order and then we subtract one from some of the numbers and then we repeat this process again. So note that you have to sort the sequence in descending order at every iteration, not just the first iteration. What a lot of people do is they just sort it at the first iteration and then they just try to decrease one like by themselves for Havel Hakimi. But when you decrease ones at every like from some numbers, then the sorting can change, right? So you'll need to again sort the sequence in descending order and then apply it again and again and again. So at every step, at every iteration, you will have to sort, not just the first iteration, at every iteration. That's the important thing. So keep this in mind, definitely. And after that, there were examples of different types of graphs which are given. I had discussed these in my problem solving sessions also. So what's a cycle graph? So cycle graph is nothing but which contains a cycle. A path graph is nothing which just but a graph which just contains a path. The regular graph is a graph in which all degrees of all the vertices are equal, etc., etc. So there were different types of graphs which are introduced in the lectures. So yeah, maybe you can look up those definitions as well. And after that, there was there was the concept of trees. So what is a tree? A tree is just a connected graph which does not contain any cycle. So connected graphs are graphs where every two pair of vertices have a path between each other. And now what is a tree? What a tree is just a connected graph which does not contain any cycle. So an acyclic connected graph is a tree. And we studied some properties of the trees that a tree with n vertices always has n minus 1 edges. So maybe I should mention that also. Tree with n vertices always has n minus 1 edges. And we have done accurate proof of this also. So yeah, if a tree has n vertices, number of edges will be n minus 1 is only in that tree. So yeah. And then came the concept of cut vertex. So what was a cut vertex? A vertex. So cut vertex in a graph is a vertex whose removal disconnects a connected graph. So initially, suppose we are given a graph which was connected, but a cut vertex is a vertex. If we delete that vertex, then the graph will become disconnected. That's a cut vertex. And then what's a cut edge? Similar definition can be extended. So cut edge is an edge whose removal disconnects a connected graph. So here also, the cut vertex is a vertex. So while we are deleting vertices, we'll be deleting the outgoing edges of that vertex also. And by deleting an edge, like in a cut edge, we are just delete one edge. By deleting a vertex, we delete multiple outgoing edges of that vertex. So there's a distinction between cut vertex and cut edge. Here we completely remove the vertex fully, and here we only remove the edge. So yeah, I hope you guys understand what I'm trying to say. So after this, in week 8 again, the concepts of graphs was continued. So in concepts of graphs here, so we studied about like the adjacency matrix representation of graph. So a graph is nothing but, like, as I said earlier, a collection of edges as well as vertices. So vertices you can just represent by some number, like you can number the vertices from 1 to n, right? But how do you represent edges? Like how can you say like an edge between vertex 1 and 3 exists? So there's an adjacency matrix representation where we store like I comma jth entry is 1 if there is an edge between ith and jth vertex, and it is 0 if there is no edge between ith and jth vertex. So that's what this adjacency matrix representation denotes. So yeah. And then we study the concept of isomorphism. So isomorphism is nothing but whether like two graphs are isomorphic if both graphs basically are actually the same graphs but have some different numbering of vertices or labeling of vertices. So basically what isomorphism intuitively is that two graphs G and G prime are isomorphic if they are actually the same graphs, but just their ordering of vertices is different or labeling of vertices is different. So if we label, so basically G prime is isomorphic to G if we can label the vertices of G prime in such a manner such that G prime becomes equal to G. So yeah, that's what isomorphism is. And then we studied what's a complement of a graph. So what's a complement of a graph? Complement of a graph is, maybe I should keep writing down these also. Yeah, maybe I think I should write down that. Isomorphic to G if there exists a labeling of. So I'm just writing more of an informal definition for isomorphism. For formal definition, you can just refer to the lectures as well or internet also. If there's a labeling of vertices of G prime such that G prime becomes equal to G. So yeah. So there's a labeling of vertices of G prime such that G prime becomes equal to G. And now then came the concept of complement of a graph. So what is a complement of a graph? It is nothing but a uh, uh, so mm, okay, so maybe I'll just not write down this definition for complement of a graph. I'll just tell you what the complement is. So what does complement of a graph denote? Suppose a graph has like a graph is noted by v comma e, right? The set v is the set of vertices of that graph and set e is the set of edges of that graph. So the complement of that graph will be uh, you you have all the vertices there in the graph. Like a graph G prime will be a complement of G if G and G prime both have the same vertices. But if an edge was present in G, it won't be present in G prime. And if an edge was present in G prime, then it won't be present in G. So that's how we define a complement. So the complement is nothing but over the same set of vertices, if there existed an edge, you just remove that edge. And if there did not exist an edge, you just add that edge. So that's what complement of a graph is. So nothing too fancy and nothing too difficult, just a straightforward thing. So based on this, some questions, like there was question in assignment also, and questions can be asked. So if a graph has uh, n vertices and m edges, then its complement will have its complement again will have n vertices only because like the vertex set remains same, and the number of edges will change because like we are removing the edges which were already present. So we are removing these m edges, and with the edges which were earlier absent, we'll be adding those edges, right? So there will be total in a graph maximum n two n choose two edges can be there, right? Because there are n vertices, any pair of vertices can have an edge between them. So there can be n choose two edges, and out of those n choose two edges, we'll remove these m edges because they are present in the original graph. So their complement should not contain these edges. So um, this is something. This is what I'm trying to say here. That uh, If a graph has n vertices and m edges, then its complement will have n vertices and n choose 2 minus m edges. So yeah. And then we covered what are bipartite graphs. So bipartite graphs, I can just say orally that bipartite graphs are uh, graphs where there can be where the set of vertices can be separated into two sets A and B, such that every edge is going from one set to another. So every edge is going from between A and B, right? And we also gave an equivalent definition for bipartite graph. A graph is bipartite if and only if. So the IFF means if and only if it contains only odd length cycles. So if a graph contains only odd length cycles, then it is bipartite. And if it is bipartite, it will contain only odd length cycles. So it works both ways. So this is an equivalent definition for bipartite graphs. And then we had the concept of Eulerian graphs. And for Eulerian graphs, what we said was, so you can look up the definition of Eulerian graphs. There's basically Eulerian graphs are graphs where there is an Euler tool. So a graph is Eulerian if and only if, this was covered in the lectures, that a graph is Eulerian if and only if every vertex has even degree, right? So if every vertex has even degree, then the graph is Eulerian, and vice versa is also true that if a graph is Eulerian, then every vertex has even degree. So yeah. And after that, we covered Hamiltonian graphs. The Hamiltonian graphs are graphs where there exists an Hamiltonian paths. So maybe I'll just so a Hamiltonian graph is a graph where which can in which so a Hamiltonian graph is a graph in which there exists an Hamiltonian path, right? And to check whether a graph is Hamiltonian, so this was basically the definition of Hamiltonian graphs, the graph in which there is an Hamiltonian path. You can look up the Hamiltonian path definition if you don't know it. I'm not writing it down. So then comes the question of how to know how to characterize Hamiltonian graphs. Like we have characterized Eulerian graphs using degree of vertices. We have characterized bipartite graphs using like odd length cycles. And so how do we characterize Hamiltonian graphs? So it turns out exact characterization is not possible. Like it is an NP-hard problem. It's a very difficult problem basically to exactly characterize. But we can have some sufficient conditions, like checking whether graph is Hamiltonian. So for this, there were some theorems, like there was one theorem which was Dirac's theorem. So Dirac's theorem just said that a graph is Hamiltonian if degree of every vertex is greater than or equals to n by 2. And then there was Orr's theorem, which was a generalization of Dirac's. So it's a generalization of Dirac's theorem. And what does generalization mean? Generalization means that Orr's theorem, Dirac's theorem can be derived from Orr's theorem. So yeah. So Orr's theorem says that for every pair of non-connected vertices, degree of u plus degree of v should be greater than or equals to n. Then we can say that the graph is Hamiltonian. But note that one thing to note here is that like these Dirac's theorem and so note that for Hamiltonian graphs, we had this if and only if condition. For Eulerian graph, we had this if and only if condition, right? Similarly, for bipartite graph, we had if and only if condition. So like if and only if means sufficient, necessary as well as sufficient conditions. But note that these theorems like Dirac's theorem as well as Orr's theorem, they are these theorems are not necessary conditions, but only sufficient. So what this means is that suppose we take Dirac's theorem, which says that degree of every vertex is greater than n by 2, then the graph is uh, Hamiltonian. So what this means is that if degree of every vertex is greater than n by 2, then graph is Hamiltonian. But it does not say anything if the degree of some vertices is less than n by 2. So actually there can exist Hamiltonian graphs where degree of vertices is where degree of vertices, some vertices less than n by 2 also. So those types of graph can also be Hamiltonian. So if you guys understand what I'm trying to say here, so it's not a necessary condition. Like every vertex need not have degree greater than n by 2. There can exist vertices less than n by with degree less than n by 2 also, and the graph can still be Hamiltonian. So basically what this means is that these theorems are not necessary conditions, but only sufficient. That if the graph satisfies the properties given by these theorems, then it will be Hamiltonian. But there can be a case that the graph does not satisfy the properties of these theorems, but it can still be Hamiltonian. Right? So note and keep this distinction in mind because I believe it's important and it can be easily asked in the exam also. So then we covered the concept of planar graphs. Planar graphs such as graphs which can be embedded in a plane. So so I'm not writing down the definition, maybe it's too easy. And then we covered the Euler's formula for the planar graphs, which is just the number of vertices plus the number of regions is equals to number of edges plus 2 for planar graphs. Right? So yeah, there was this formula, and yeah, after this, the graphs part was over. And then in week nine mainly focused on generating functions. So I'm not going to go into too much detail for generating functions because like almost everything based on generating functions has already been discussed in sessions and stuff. Maybe I'll just maybe give you an example of generate. So maybe I'll just give you some expressions like what does this mean? So like we have already discussed it in problem sessions also. So generating functions are just like infinite functions and they use essentially these types of formulas. So like this 1 upon 1 minus x, this can be actually expanded as 1 plus x squared plus x cubed and up to infinity. And similarly, like as I had discussed this in problem solving sessions also. So this is one generating function. Similarly, there can be multiple generating functions. Another important function can be like suppose we differentiate both sides. So what we get here is 1 upon 1 minus x when differentiated will give me 1 upon 1 minus x whole square. So this will then be equals to, so differentiating this side will give me this expression. And here differentiating 1 will give me 0. This x will give me 1. Then differentiating x square will give me 2x. X cube will give me 3x square plus 4x cube and so on till infinity. So yeah, so these are two types of generating functions. There can be more generating functions. So yeah, I'm not going to go into much detail, but yeah, so these were some sort of generating functions which we discussed, right? And then in week 10, mainly the concepts related to advanced counting, like counting was earlier covered in like week 1 also. But now in week 10, there were some more advanced counting methods introduced and to like count different sort of stuff. So like the principle of inclusion exclusion, like principle of inclusion exclusion was covered here, which just states that the like suppose the how to write basically like A1 union A2 union A3. Cardinality of A1 union A2 union A3 will just be cardinality of A1 plus A2 plus A3 minus A1 intersection A2 minus A2 intersection A3 minus A1 intersection A3 plus A1 intersection A2 intersection A3 or something like that. So yeah, so you can just look up what's the principle of inclusion exclusion and yeah. So and what's the use of principle of inclusion exclusion? So one case we saw was which is very important generally is like counting the number of onto function. So suppose we have been given two sets A and B, and we need to find out how many onto functions are possible from A to B. So using inclusion exclusion, we can do this. You can look up in the lectures if you want, like how do we do this? But yeah, it can be done. So this was one very important use case. And after this, there was something concept which was covered along lines of root polynomials. So root polynomials was nothing but so basically root polynomials in one coefficient in root polynomial was basically, suppose we have been given an m cross n chess grid and we want to find out the number of ways of placing like n rooks such that no two rooks basically can kill each other. So in chess, rooks only move along rows or columns. So suppose its most general formation is that we suppose we have been given like k cross k chessboard and we need to place k rooks so that no two rooks intersect with each other or maybe they can kill each other. So that's the formulation. So we can just generally see in that example, basically the answer for that case would be k factorial only. And why would that be the answer? This will be because uh, for every row, we can select one unique column. If two rows have same rooks in the same column, then those two rooks will kill each other. So every row should have a different column attached to it. So that's why like there will be k factorial such permutations. So the number of ways of placing k rooks on k cross k chessboard such that no two rooks kill each other will just be k factorial only. And then we try to generalize it to an m cross n chessboard by using the concepts developed along these lines only. So yeah, so these were group polynomials. And after this came like week 11 in which we talked about recurrence. And I believe I talked about it a lot in my sessions also. So we first of all studied what are Fibonacci sequences and how to solve Fibonacci sequences. So if you guys remember, like Fibonacci sequence is something like Tn equals Tn minus 1 plus Tn minus 2, right? So we replace Tn by x squared, Tn minus 1 by x, and Tn minus 2 by 1. And then we solve the equation x squared equals x plus 1. And we get the solution of x, the value of x, and then we try. So we write. So suppose we get the solutions as alpha and beta. There will be two solutions for the quadratic equation. Then we write the solution as c1 alpha to the power n plus c2 beta to the power n, and then we find c1 and c2 using base conditions that t0 is 0 and t1 is 1. I hope you guys remember. I'm just orally telling you all of this because this has been covered in lectures and I've extensively covered this in problem solving sessions also. So you can look up the whole procedure in those sessions. And then there was this problem of tower of Hanoi, which was also discussed that suppose there are three rods and there are n weights given, and we need n weights which are put in like the descending order, which are put in the descending order in first rod, and we need to put these weights now in the second rod, transfer these weights in this form onto the second rod, and we should follow the constraint that a heavier weight should always be below a lighter weight. Like if you guys understand what I tried to say, just like it's just a Tower of Hanoi problem only. So we obtained a recursion for this also that t of n equals to 2 times t of n minus 1 plus 1 or something along those lines. So yeah, so from that we obtained an exponential solution that Target will be solved in exponential number of steps. And then there was in using recurrence only, we try to sort an array. We use the technique merge sort. General sorting generally takes normal sorting techniques take order n square time or n square steps, whereas merge sort took only n log n steps. Here, how the recursion was, it was something along lines of like we halve the array, we sort half the lengths of each array at each step. So suppose there's an n length array, and what we do is we divide into two parts of n by 2 length each. Then we sort those two parts individually and then merge these two in linear time. So its recursion was something like t of n equals to 2 times t of n by 2 plus n. And for that, we saw that the solution was, I'm just doing all of this orally because all of this you can find in lectures as well. And from this, we were able to see that this comes out to be done in n log n time. From this, we get that merge sort takes only n log n steps. And after that, there was this the last week focus the new concepts covered in last week. Basically, last week also focused on some recurrence, but the new concept which were covered was basically on group theory. So what are subgroups and what is Lagrange theorem? So maybe like since Lagrange theorem is important, I'll just write it down. So order of a group. So first of all, we covered what's an order of a group. So order of a group is nothing but uh, number of elements in the group. So order of a group is generally defined for finite groups. So order of a finite group is number of elements in the group. And then we define what are subgroups. So subgroups are generally subsets of the group, which are groups amongst themselves on the same operator. So over the same operator is subset of the group over the same operator. So a problem in assignments was based on this property also. So know that this same operator term is very important. Suppose if you are so in a group, you generally define a set and an operation, right? And an operator basically. Like suppose the group was defined over the operator addition. So a subgroup should also be defined over addition only. Like you can't say it is a subgroup over subtraction. Then it won't be a subtraction. Then it won't be a subgroup basically. So a subset should be a group. A subset should be a group over the same operator. So subgroups are nothing but subset of a group which follow the group properties over the same operator. Maybe a better definition can be found out through the lectures, but the core idea remains the same, that a subgroup is just a subset of a group which follows the properties of the groups, which are like closure, identity, and everything over the same operator only. Like if the original group was defined over addition, then the subgroup will also be defined over addition only. So this is important because like suppose a question comes in exam, or maybe just not from exam perspective, that the group was defined over addition, and then yeah, an option comes where the subset is actually following the group properties, but the operator is subtraction. Then even though it's following the group properties and it's a subset, it won't be a subgroup because operator needs to be same, right? So some sort of problem I covered this in problem solving session also related to this. And finally, in group theory, like there was this Lagrange theorem, uh, which just said that order of a subgroup divides the, or maybe is a divisor of the order of the group. Some questions can be based on this also. Like basically, suppose order of a group is 10, then order of its subgroup can only be a divisor of 10. So it can be like 1, 2, 5, or 10 itself. Like if it is 1, then it's just the identity subgroup, which is trivial. And similarly, when it is 10, it is the group itself. So these two are called generally trivial subgroups, the identity subgroup, which has order 1, and the subgroup itself, which is order of the group itself. So other than that, the other subgroups are generally called like proper subgroups. These two are trivial subgroups and the other are called like proper subgroups. So like there can be two proper subgroups for a group of size 10, which will be of size 2 or size 5, right? Uh, I hope it's clear to you guys what I am trying to say. Suppose the question comes, which of the following cannot be order of a subgroup of a group of size 10? And the options are, there was some assignment question based on this also. And the options are like, let's say 2, 5, 1, and 6. So the answer will be 6 because uh, 6 does not divide 10. So yeah. So yeah, I guess this sums up the 12 weeks of lectures, the theory of lectures, which was covered, and over and all the types of questions which we discussed in related to those lectures in the sessions also. So yeah, I guess this sums up this summary session from my side, guys. So this was like, at least from my part, the last bit of interaction with you guys. So yeah, we interacted over like 13 weeks. So it was over 12 weeks and 13 sessions. So it was fun interacting with you guys. So thanks a lot for attending the lecture. So if you guys have any doubts, maybe we can take up 1 or 2 doubts also, since we can only take up 1 or 2 doubts right now because we are speaking over time. So if you guys have any doubts, maybe you can ask in chat, or if not, we can close the session. And like, thanks for attending, guys, and thanks for bearing with me for these 12 weeks. So yeah. So if anyone has any doubts, you can ask me in chat, or else I'll just maybe close the meeting since we are done from my side. So I'm just assuming that since no one is typing anything in chat, so and no one has any doubts. So yeah, guys, it was fun interacting with you, and hopefully I'll see you guys in the next semester as MTA for other course also. So yeah, good luck for the exam, guys, and goodbye.